let's get started here. So thank you for your time today. Appreciate you joining us. We are happy to have Robert Bellis here today from Elsica, and I apologize if I mispronounced the name. I am American and went to public school. I apologize. This is part of iNEMI's Tech Topics series of webinars in smart manufacturing. We also have other series in sustainability, PCB, and other topic areas. These are the current calls that are scheduled here over the next month or so. If you're interested, I would ask you to please go to inemi.org/events to register for those events. A little bit of hygiene for today's call, just to let you know, you should all be on mute. If you're not, I will try to mute folks just to keep the line quiet. If you have questions during today's call, I would ask you please use the chat feature, and I will collect those and we will ask them of Robert after the end of his presentation. If we don't get to them, I will try to get them answered over email with him, and then when we send out the recording, we'll make a little FAQ sheet with some of those questions if we are unable to get to them into the recording. You may have heard I said recording, so we are recording the session. We will be sending the recording and the presentation out after the session, probably sometime next week. But with that, you're not here to hear from me. I'm going to turn it over to Shekhar Chandrasekhar, who is the CEO of iNEMI, and he's going to introduce our speaker today. Shekhar?
Yeah, thanks, Mark. Welcome, everyone. Good morning, good afternoon, good evening, wherever you are. I'm excited to kick off today's session in our Smart Manufacturing Tech Topic series, where we spotlight how digital transformation is reshaping electronics manufacturing. Last week, you heard something about product security. Today, we are focused on a slightly different but related topic. We are focusing on a process that is essential and sensitive. It's copper plating in PCB manufacturing. It's a step where design, layout, and production setup must align, because even small missteps can lead to scrap, inefficiency, and wasted resources. And this is really important because it aligns with the core purpose of why iNEMI exists, which is de-risking technologies to support high-volume manufacturing. So, good news. With digital twin technology, we can now simulate plating behavior from the design phase, from testing and optimizing before production begins. This shift empowers designers, reduces overplating, cuts down on destructive testing, and drives sustainability. In this session, we will explore how design and setup impact plating outcomes, how digital twins improve yield and reduce waste, real-world examples from leading manufacturers, and why plating performance starts with design. This is smart manufacturing in action, where simulation meets strategy and collaboration drives results. Welcome again, and welcome, Robert. Thank you for taking time to do this webinar. I really appreciate it.
Sure. Thank you for inviting me to have this presentation.
All right. I'm going to stop my share, Robert, and let you take over, okay?
Okay. I will take over then. So if all is good, you should see a screen with digital twin is digital win. Is that okay?
Yeah, it looks great.
Okay, perfect. Thank you. So the topic of the day, it was already mentioned a few times, is about simulations and the impact of, or potential impact of simulations on sustainability and, let's say, the plating process in general for PCBs. So what I would like to focus on, or as a bit the schedule of my meeting here, or presentation here, is the following. So as for most, I don't know, of you, the company Elsica might be unknown. I will have one slide, so don't worry, I'm not going to talk a long time about that part, but I'm going to talk about, what Elsica as a company is about, so that you have an idea how we came to this type of solutions. I will then explain a bit what the plating process is. I know there is a whole bunch of experts here in this audience, but some of you may not. And nevertheless, I don't think it hurts to pinpoint a few, let's say, hot potato items, like we say in Dutch, related to plating. And then find out or explain how design impacts this, how manufacturing impacts this, and you can, with simulations, indeed reduce the number of iterations, avoid that you create waste, etc. And then explain how some of our customers, I can obviously not disclose too much in that area, but you will see that there are a few very known names in this list and how they benefit from this approach. As Mark already indicated, during the talk, you can absolutely ask questions, but to make it simple and organized, put them via the chat, and we will then, in the end, in the conclusion part, go over that. So, when we talk about ELSICA, let's start with the name because a lot of people struggle with the name. So ELSICA is basically the abbreviation of electrochemical system calculations. The company was founded in 1997, so we're quite a while in this business. And our business is providing solutions, simulation solutions, that basically simulate virtually any electrochemical process. That's the main goal of our company. In that sense, we have two separate business units. One is surface finishing and one is corrosion protection. So you could see surface finishing as the unit that, let's say, supports all the businesses that, the processes that put metals on a surface. While corrosion protection is then more about avoiding that metal is taken away by corrosion and how you can counteract and avoid that you have issues in this context. So, but now the talk of today is about PCBs and plating the copper layers. So this is definitely the surface finishing area, and that's what I'm going to focus on for the rest. So when we talk about ELSICA PCB, the plating industry in general, let's start with what is plating. Simply put, plating is the process where you grow a copper layer on your traces and inside the holes. So why do you need that? You need that to have a good signal, let's say, transportation, if I can call it like that. And it needs certain, let's say, thicknesses and widths that need to be very well respected in order to, let's say, make this PCB function that the designer has in mind. And so you need a certain signal strength. You have to avoid things like crosstalk and all these kind of things. So the thickness of the PCB, of the copper layers and the thickness of, let's say, the copper inside the holes is extremely important to have in the end an operational unit. Now, that thickness is, let's say, added by the fabricators using an electrochemical process. Now, an electrochemical process has a couple of components, and I think it's good just, let's say, maybe as a refreshment to again be aware of what you have in that context. So when we talk about an electrochemical process, an electroplating process, you will typically have, let's call it a tank or a box, whatever you want to call it, that has some anodes, which in this case will be typically copper-based anodes. You will have an electrolyte and you will have cathodes, which is in this case your PCB or the panels that needs to be plated. Now, in order to accelerate the process, because I mean it's modern times, we are all in a hurry, so we want to grow that layer as quickly as possible. You will use or apply an electrical source or a rectifier to accelerate this process. Now, the result of your plating depends on a whole number of things. And one of them is, for example, the panel layout and the number of panels you put in the tank. So some people also call it your rack layout. So basically the configuration that your fabricator is using in the tank to plate the parts. He can apply some toolings, etc., but that would lead a little bit too far now to explain all that. Once you have these panels, then although those might be identical and produced in different fabricators, you may have different results because of the configuration that the fabricators use. Anodes, for example, come in different shapes, in different positions. Your tanks will be different, the metal type will be different. So yet another step of flexibility here. In this case, we're talking about copper plating, so we're good. But how does this copper behave given certain conditions? Is it in new state? Is it in depleted state? What's the flow condition? So again, a number of variables that make it more difficult to understand what's going on. When we talk about your electric source, where we see that though a lot of DC is used, we also see that a lot of pulse programs are made or being applied, and that is something that is quite challenging, as you need to find the right, let's say, pulse program to make the process the most effective. Apart from that, you have the process time that obviously has a role. The longer you plate, the more thickness you will have. In the end, we should also think about the plating tank dimensions, anode, cathode distance, and all these kind of things. So a whole lot of parameters that play a role here. So conclusion, it's fair to say plating is a very sensitive process. Now, you may think as a designer, why would I care? I mean, that's a supplier's, let's say, problem to solve. But you as a supplier, you have one of the big keys in your hand here. If your basic design of a PCB is not good, you, let's say, make it difficult for all the rest in the chain. And as I try to put here a bit visual, I mean, if it's not done properly, you just pull out one block in this case and the entire thing collapses. So you have to be aware that this process exists and will be needed, and you as a designer have an impact on this. Now, having that said, from the process point of view, how does today the market trend look like? And how does that impact your technical constraints that you may have? Well, first of all, and I'm just taking one example, there is obviously many more. It's clear that there is a big push to push more and more, let's say, components and elements on a more compact form. So it means you have high density technology here. So that means you need to push more things closer to each other. You have thinner layers. And that means you have less spacing in the end between the traces. And that may have as a result that during the plating process, things start to interact with each other, or you have extra issues that you may not initially have thought of. So to illustrate that, so if you assume in an old design, well, old, I mean, everything is relative, time flies nowadays. But if you have a certain layout where you have a certain distance between your traces, one thing is clear, everything is coming compact, so they're coming closer to each other. Obviously, you need to see that, I mean, these things are not coming too close that when you grow a layer that they will touch each other. Another problem is that you have, as a supplier and as an end user, you have some, I would say, tolerance levels that you would accept. And you say like, okay, if we make a design and we take these kind of tolerances, we will be good. So even if there is, let's say, some variation in layer thicknesses, we will be good. But if everything gets more compact and you go, for example, in the pressing design, you will have potentially an issue as before when you could, let's say, have more thicknesses in your total layers, and now things have to go more compact. If you overplate some regions, they may start, let's say, touching other different layers that they are not supposed to. And as a result, you have, let's say, short circuits or boards that are no longer functioning. And since we're talking about sustainability here, I mean, this is definitely not good. I mean, you spend all the efforts to produce a certain, let's say, part of your bare board, and then you find out it doesn't work, and you have to it's crap. So let's try to avoid that. So overall, what you need to do, you need to be more in control of the tolerances and better control your process to avoid that you will get into these type of issues. So look now at how the process typically works. So you start from a design. This is typically done by, I would say, let's call them the end users. I mean, the companies that actually need a cell phone, that need an ABS system for a car, some control for whatever. They design, but they typically do not produce. So when you start production, you send it over to your fabricator, and the first thing that will need to happen is you need to build your bare board, which needs to be, I would say, consistent in the quality, and there will be some checks done to see that this is done and produced properly. As a next step, you will do the assembly and you start adding the final tooling to finally integrate this in the total end product, which it can be like in this case, like a dashboard or whatever. Now, what we want to do is make sure that we add a DFM check, or design for manufacturing check. When you do this, you could potentially identify issues earlier before you actually go into the next step. And obviously that continues between all these next steps as well. Now, when we talk about DFM and you do it at the design stage and you find an error, that's something you can typically fix in a couple of days. Why? Because if you're using your design tool and in your design tool, so obviously you first do your design and then you do a check for manufacturing, you might already find out some issues. And since you're still designing the tool and checking things out, everything is in front of you and you can make the necessary changes, make some variations till you're happy and continue that process very quickly. If your design makes it to production to then find out that your design is no good, typically you have lost weeks. Yeah? And not only weeks, because your supplier, he will do his very best to try to build the part that you're asking for according to spec. So he has for sure done a number of tests, spent a lot of energy in order to do all these tests, try things out, and then have to scrap everything to then come back to you and say, sorry, I cannot build it. You need to make some changes to your design. Yeah? So let's try to avoid that. And needless saying, the further you go in the process and the later you identify problems, the more expensive it will become and the more, let's say, resources has been used in vain, you can say. So how are we going to address this? You can address this in several ways, but simulations is for sure has come to a level that allows you to actually upfront validate certain, let's say, aspects of your design or your layouts or your production process so that you can check before you go to the next step that what you are doing in your step is going to be, first of all, well for your step, but also as much as possible avoids problems later in the process. Yeah? And what I'm talking about here is we are basically going to do two things. We're going to find out how your copper layer thickness distribution will look like given a certain design, given certain configurations, etc. on one end. And we will also try to find out if we can find a mitigation strategy if needed to ensure that we improve the uniformity of your copper layer thickness distribution so that you do not have to overplate where you spend a lot of energy to grow a layer too thick, to then have to again spend a lot of energy to etch the areas away that have over thickness or too high thicknesses. So knowing things earlier will help a lot. The goal here is we want to be faster to bring your tools to the market. You want to make sure that your development costs are kept under control and you have a better view on what's going to come later as well. You want to make sure that your designs will be more robust. And with robust, I'm not only talking about one PCB, but as you all know, when you produce PCBs, your PCBs will be put on a panel. And obviously, well, obviously, maybe not obviously, but in reality, you will see some variation on the same panel over the different PCBs. And then you have different panels on the flight bar, which again have variation. So in the end, what you want is as minimum as possible variation to have consistent product and also to avoid material waste. So let's now look how simulations actually can help. Now, assume you're a designer and you make a certain layout. What you will typically have on your screen is not something colored like this. You will have something like all in black or whatever color that you prefer for your design stage. Yeah? You're typically working in an ECA tool, and well, I'm not going to put commercial names here, but you know what kind of tools I'm talking about. If I'm an expert in design, I'm an expert typically in all the electronic components and the signals and all these kind of things. I'm not necessarily an expert of plating. And even if I'm an expert in plating, it's not so obvious to predict how your layer thickness distribution on such a design will look like. Luckily, there is software that will allow you to predict this. And what you see here is a result of that. And what you will get is, let's say, a color map or a heat map that shows you the layer thickness variation over a PCB. Yeah. What is a bit specific and that you need to know to properly interpret this is you can put a scale from 20 to 28 in this case, using some, let's say, color heat map. But then you have, let's say, a specific color for everything that is too thick or not thick enough, so that exceeds your range of acceptable specifications. Yeah? And what you can see now is that in the areas where you have a lot of copper, some areas are too low. And in the sparse areas, there is, let's say, way too high thicknesses, and that will result in potential problems and could lead to, for example, growing layers that these two traces, for example, would touch each other. Yeah? So you don't want that. Now, you can say like, but okay, I know, I mean, these things are isolated. I know that this will be a high value. Well, for the visual traces, that's already a challenge. But believe me, if you have, let's say, a few thousand of holes in this on this PCB as well, those holes have a tremendous potential impact on your layer thickness distribution as well, that this technology will account for and are extremely difficult to, let's say, predict manually. So ideally, this layer thickness distribution is as uniform as possible. And what we would like now to achieve is that we move, let's say, from the design on the left to the design on the right. And you can say like, okay, but that design is exactly the same. Yes, the electronic design is exactly the same, but you see that the colors are different. Yeah? Now, this is not saying like, okay, we have different colors, so you're good. These colors are obviously, let's say, a result of something that we added, and that is copper balancing. So copper balancing is, let's say, a technique that allows you to, let's say, fool, if you want, the plating process by adding copper areas that are not part of your electronic circuit, and as a consequence have to be at a certain distance of your electronic circuit to ensure that they do not interfere with it. Yeah? That manipulate the layer thickness in the end by changing what is called current density on the PCBs. The trick is, how do you know where to put these copper balancing? Yeah. So typical these ECAD tools, they have a way to, for example, put a kind of a hatch over this entire PCB, but that's not necessarily the best way to proceed. The technology that we apply is a technology that will only, let's say, focus on the areas where it's needed. And that's why you may see some, let's say, copper balancing that you may not yet be used to. If you wonder like, okay, if I do that, so what's the impact on the process? Well, we did a test with this. So we actually had this design that you saw on the previous slide. So on this slide, we really had it manufactured in a plating shop. They designed a panel layout for that, and we produced that version. And what we saw was that the CPK, so the CPK is the productivity capability index or production capability index. So it's a kind of indicator that tells you how well your process is able to produce the parts within specification. That production process has gone up with a factor 2 compared to the original design and the optimized design with copper balancing. Again, we're talking about copper balancing. We're not talking about changing the design itself. Yeah? And you can also clearly see that. Here you see these magenta colors, and here they are green. Yeah? Now, of course, I hear some people say like, yeah, okay, but I'm a designer. I don't have time for this. I already need to check the signal integrity, impedance problems, heat problems, and all these kind of things. And now I also have to check this. So how to address this? Yeah? Well, there is software that you can use in an interactive way, but it's of course also good to know that all these things, all this technology can simply be integrated in your ECAD or your CAM environments, because this works for one single PCB, but it also works for a CAM environment where you would add copper balancing not only, let's say, not inside the PCB area, but outside your PCB area. And the flow that you should look at it, that this would work is, you enter your design or your CAM layout like you normally do. You then press a button. In background, there will be a number of tests done. The data that is needed will be extracted. Computations will be done. And then you will get, we call it the traffic light system here, a green light, which means, okay, this layout, you're good. Just ship it to your supplier or ship this panel layout to production. A yellow light means like, this is not good, but if you apply the copper balancing that we suggest, you're within the specification levels that you ask for, and then you can proceed. The good thing is you're still in your ECAD environment or in your CAM environment, so you can still run all the other tests that you like just to ensure that there is no interference with whatever. If it's a red light, it means, well, don't bother going to the next step because this will not work for plating at least. Yeah. So to be very clear, we are only checking the plating step here, right? So that gives you a lot of, let's say, input very early in the process. Nothing is built physically. You don't have to spend any, let's say, energy in building parts, in accessing production lines, in waiting till your supplier or the production is ready to test things. You can do this simply on your computer. That's the design stage and the panel layout stage. Once you pass this, it's time to actually build the bare board manufacturing or go to the bare board manufacturing step. So now we are going to the supplier who actually has really a physical line that you know that has certain, let's say, chemicals that he uses, certain configuration he uses, etc. So we call, let's say, the mapping of all these specifics a digital twin. So we make for this specific environment a digital copy of what you will see in reality. So that means we will include in the simulation part real things like the physical dimensions of the plating cell, the geometry of the anodes, the specific behavior of the electrolyte that's being used, because one copper bath is not the same as another copper bath, yeah, or may not behave in the same way. We will also do investigations like if you're using a certain pulse program, how does your electrolyte behave, etc. Yeah, all this is put in a digital format and made available for the operator in a technology that then allows him to upfront do an analysis of a certain configuration. So if I'm a fabricator, I do not have to wait till I get your PCB design in my hands and wait till I actually produce a physical panel to do a test. I now do that on my computer system. So I can say like, okay, for this specific design, I think a certain configuration will work. I enter it in the system on the computer. I don't go to the physical production yet, and I check things out. I will then find out, okay, was this good or not? Do I need to find a better way? Should I further tune? And then you can do what we call the mitigation strategy. So you find or evaluate different things that you would, in theory, do. I'll rephrase this, that you would do when you actually would do production. You see that by measurements, you're not getting the results that you wanted. Then you may decide to, for example, add a shield as an example. You need then to build the sheet, start the production again, do all these tests again. Well, all this cycle, that's something you can do in the software. And to illustrate this, here is a typical example of such an evaluation. So what does this mean? In this case, I have a panel that has like, I don't recall, 35 or something PCBs per panel. They are all identical, the panels. I have 3 different panels in my production plant. But what I do see is the typical edge effect that you will see in production. Yeah? That means that the areas that are on the outside, those are indicated here in red, they will get more deposit than the areas in the inside. So that also means when you look, for example, at this PCB or that PCB, that this one will look entirely different and that the variation may be too high. So that's something you want to avoid. So your supplier can have some, let's say, specific countermeasure that he can use. For example, it's just an example here. He could use shields and current robbers. So shield is something that will redirect the current in the plating cell, while a current robber is something that is active and it will be plated, but by having this copper wire typically too close to your panel, it will take current away from the panel underneath. And as a result, you see that at the top, the red areas are gone, and the sides here have now less thickness and it looks more uniform. Yeah. So that's the goal of this process. If you have to do this manually or physically, it's a tedious process. So first of all, think about this. If you do a test and you get a certain outcome from your production, how do you know where you have to measure? How do you know where the critical hotspots are? Yeah? Simulations tell you that immediately. Yeah? So for quality control, this is really a blessing because now you know where to measure. Yeah? And that brings me to a topic that is called P points, or probe points that you put on the panel for production. Typically, you put a probe point on a production panel, and you will do a cross section in that probe area, because you don't want to, let's say, ruin the actual product, the PCB that you want to sell to your customer. But the problem is your test coupon will only show you what is relevant on that specific area. So to say something, if your test coupon is here, it will tell you, okay, you have very high values, but it doesn't say anything about this one. Yeah. So what you could do is, by simulations, in the end, when you're finally done, you can still do a physical test in the end and feel happy. Check the test coupon, do a cross section to see what the physical layer thickness is. Check in the simulation what the predicted layer thickness value is, and then you can, let's say, magnify that to all the values on your PCBs over all the panels to ensure that everything is within spec. To give you now a feel of what you can save with this, yeah. Assume I have a certain configuration. I'll stick to my 1x3 layout, so 3 panels in a row. I put them in a system between 2 anode sets, like a typical production would look like. I would get a certain, let's say, variation. Yeah? And what I did here, I specified a certain maximum that I would accept, and I color them, and this is what the simulation can do for you, show all the areas that are outside my spec in black. Yeah? So you clearly see there is a lot of, let's say, problems here. Yeah? There is a lot of areas that are out of spec. Then I decide to make some tooling. Yeah? And some of you might now be a bit surprised by the type of tooling, but I put some shields with some holes in there at certain locations. Yeah? So it can really go quite far if you like. That can also be quite well automated if for those who are interested in that. So I would say if you're interested in this, contact me separately on this topic. But by applying these shields, I get a better distribution. Yeah? And to give you a more a feel on what that physically means, so with this specific layout compared to the original one, I have now 61 of the total amount of PCBs that is within spec, and it was, sorry, I have to rephrase, I raised the amount of PCBs that are within spec from 61 to 83. So otherwise put, my scrap goes down from 32% to 8%. Yeah? So with the same amount of energy I'm using here and the materials that I'm using, etc., to produce this total amount of panels, in the end, I have 83 good products compared to 61 from where I was starting from. So just think about that part already. Yeah? Another thing is that because I better control the current density and the layer thickness, my CPK value, so the values that indicate how well my process is in line with the specifications, goes up with more than a factor 2, which is immense. Yeah? Also important to know is that the PCBs that are not fully in spec, well, they are, I call it near misses. And what I mean with that is, assume my maximum is 28, they might have, because it's a computer here, so when we tell a computer everything above 28 should be black, well, if you have 28.00001 or 5000, it will be black. Yeah. So what I'm trying to say here, with this optimized environment, the parts that are outside specification, they are outside, but not excessively outside. So that might still be something with some negotiation with your end customer that could still be accepted. Since we're talking about customers, let's take a few examples of people using this technology already. And I'm using both fabricators as well as end users. So Calumet to start, it's a fabricator in Michigan in the US. They have very high-level boards that they produce, and they are using our software to predict the layouts before they actually produce them. And as you can see, the first pass yields are much better than they have compared to the situation that they had before. I cannot disclose more information. You see the contact person there, so if you feel like this is something you would further like to explore, be my guest to contact this person, but that's all I can unfortunately disclose. I hope you appreciate that we respect the confidentiality here. Another customer now from a completely different point of view is Safran. So Safran is a company that is active in aerospace and defense. They use our technology in the design stage. So they use our technology to check that their design is fit for the purpose, and if needed, copper balancing will be added. It's a statement, it's not me telling you this, but one of the senior experts there at Safran who says that they will be making savings or are making savings between 5 to 15%, depending obviously on the design and the complexity that they have. But also very importantly for them, they also really care about sustainability and making sure that products are produced with the minimum, let's say, resources required. And obviously in plating, where we can have a lot of variations, it's a bit of, let's say, painful that you first have to spend a lot of energy to overplate some areas, to then spend again a lot of energy to take the excessive areas away by doing the etching. Yeah? So it's something that, I mean, is clearly something that for Safran and other companies, obviously, is a very important aspect as well. Another example here is Roden and Schwarz. So Roden and Schwarz, it's a fabricator in Europe. They're also using our technology in the copper balancing, this time not inside the PCBs, but on the panel level. Yeah? And that allowed them to have better manufacturing quality and material savings. And just to explain that a little bit, what you see here on the left is a panel layout as it would typically be produced by a standard CAM tool, where you would say, okay, I put my two, and that's what you see here, of course. You see it's two big PCBs. They put two big PCBs and then use standard hatch from the CAM system to fill up, let's say, the white space to have a bit more uniformity. But by using this and looking at the simulation results, you see that in these corners here, you still have quite a, let's say, a big amount of overplated areas that could lead to problems. When you look at the balancing that our system adds, you see that it's clearly, let's say, different. Some areas are dense, some areas are less dense, etc. But you can also see that these red zones here are gone, yeah? Or at least reduced. Yeah? Now, that obviously, just like the standard balancing in a PCB, you can only add copper balancing if there is sufficient space to add it. Yeah? I mean, we should not be shy on saying that as well. So if there is space, and typically on panels you have space between the PCBs, or you try to have some space, applying some copper balancing can help a lot. And by doing so, by having less, let's say, overplated areas, they saw that in the stripping process, they had less issues because the photoresist was still pinched in some cases because of the overplating, while it was not pinched in the end, and have, let's say, again, an operational bare board again, by having a more uniform controlled process. So summarized, and I will jump to your questions in a second here, just what I want to say is the following. Yeah. So first of all, you may laugh a bit maybe with what I'm saying here, but shift left, make it right. I think that's a very important thing. Anything you do early in the process is better. Yeah? Whatever you solve at the start is cheaper to fix. That means also designers should think about this. It's not always only the fab problem. Yeah? Don't make your own life difficult and more expensive by throwing your design over the wall to the fabricator and hoping that they can fix it. And maybe they think like, I cannot say something to my supplier, to my customer, because maybe they go to someone else. I mean, consider your fabricator as your ally, not as, let's say, a cost that is necessary to produce the part. Yeah? My main message here, talk to each other and make sure that you can collaborate and share information as soon as possible to solve problems as early as possible. One end. Secondly, I know that in some areas of the PCB manufacturing, simulations are not yet so commonly used. Don't be afraid. Yeah, it's not to give you extra work, it's to save you time, and it can result in serious savings. Yeah? And then, because this was about sustainability also, I would say spend your energy wisely. And I mean it a bit dual. Yeah, of course, spend your energy wisely on only spending energy where it's needed and only, let's say, put the layer thicknesses that you need and avoid overplating and again spending time to get rid of it and avoid the scrap. But it's also spend your energy, and now I mean it mentally, wisely as well. Yeah, why would you spend days and days and days on trying things out while computer things can do that for you? Yeah? So let's try to be all as efficient and effective as possible, both mentally as well as in reality on the real things, and go from there. And that concludes my presentation. So I look forward to your questions or reactions on this topic. Thank you very much.
Great, thank you, Robert. There are a couple of questions in the chat. Let me see if I can unmute folks. So Amba, you asked the first question. Let me
unmute me. Yeah.
There you go. Yeah, we got you.
Yeah.
Ask your question.
It's a very great presentation. So when I conduct IPC course, I tell people very clearly that a via reliability is as important as people spend a lot of time on schematics. They do DRC, they check schematic, they check layout. But when it comes to via, they have taken it for granted. And sometimes the specifications also are very ambiguous. So, I mean, the presenter told at the end that even the supplier is afraid of losing the market. They try to do something without even the designer being aware of. Yeah, that's a very great thing. I mean, since I mean this thing should have happened 10 years back. I mean, in my opinion, but better late than never. I think this is going to be a game changer. This kind of application. Yeah.
That's also the reason why I mentioned in the beginning in one of the slides that when I said like, when do you apply this? I said like, okay, designers, I also put RFQ there and then CAM and manufacturing. The RFQ is not by accident there. And the reason I say that is twofold. First of all, if you're, let's say, the person who designs a certain layout and you need a quote for your end product, obviously you look for a supplier, and typically people look at cost. I mean, the cheapest has an advantage, let's call it like that. Yeah. But how do you know that your supplier, whether it's now the cheapest or not, is able to actually produce the part? Yeah? So that's a question. Yeah? So if you get objective information that helps you getting a preview of how your design or your PCB will look like in a certain factory given a certain configuration, that would of course be very helpful. Yeah? And that's something that can also help both sides. I mean, if you're a fabricator and you can show your potential customer like, okay, this is what your layout will look like in real production. But if we want to do it right, we have to put some tooling or whatever. Yeah, and then there will be some extra cost, but look, then your quality is more consistent. That's, of course, very important information for you as a end customer, because in the end, what do you want? You want an operating product at a fair price also, obviously. But if you then have two suppliers and one has price A and the other price B, then it's not just price, but also you get a preview on the expected quality. And that also helps, of course.
Yeah, only one more statement I want to make. With that, I don't want to hog. There are other people in the review. See, what's happening in the industry is there are two things. It is a two-way street. The PCB vendors somebody there should also know the design, and even the designers, there should be somebody who knows the fabrication. They don't do it actually. People don't invest on that. Number one. Number two, either you get into a vendor lock-in where a specific design rules are tried to be applied to a lot of designs. That's one thing. The other thing is even the PCB vendors at the RFQ stage, they project something, and when it comes to when they get the real PO, the TQs, the entire language changes. I mean, once they know that they're going to really do this project, they're going to add some more parameters or some more questions. this is the one which is not bringing some sort of a healthy data exchange between the OEMs and the PCB fabricators. If this is improved, then things will change. Yeah, that's it. That's my feedback.
Thank you.
Thank you very much. Joe, are you still here?
I'm still here.
There you go. Would you like to ask your question, sir?
Yeah, sure. So you kind of touched on this a little bit, but I wanted to get more information. So you showed an example of no copper balancing, and then you had kind of selective copper thieving that you would put in certain places. And I think you actually mentioned that putting it everywhere wasn't necessarily the best approach.
Exactly.
Did you do any testing, and how did that come out? What was the impact of putting thing everywhere you could possibly put it on that layer?
Well, if you put, let me have to formulate this. So when we look at plating, the plating process itself is driven by copper density, by active, current density. Sorry, I'm mixing names here. So let me rephrase. So the plating process is driven by current density. Current density is driven by what we call active surface, right? So if you would put, and to make it now very simple, assume you do panel plating. You don't have a pattern, it's just full copper. Yeah. But so there you could say, okay, that's a similar thing. That's the most extreme version, if you want, of filling your panel. You would expect a completely, a completely uniform deposit, right? Now, if you do this on a vertical line, you will not have uniform deposit because the parts on the side will see local different conditions compared to the one in the middle, to say something. Another thing is there will be potentially holes. Yeah? Now, by adding holes, and holes are quite important here, certainly with multi-layers, and that's what we see more and more, multi-layer, more complex environments. We see that the active copper fraction, which would be simply put, if you have like a panel, no holes, and everything is filled, you have 100% copper fraction. But if you have a lot of holes, it can very well be that you have like 120% copper fraction in some regions. Why? Because the whole walls and the bottom of the hole, if it's a blind fire, also is active and will manipulate the process. Yeah? So to come back now to your question, like if we just put a hatch all over the place, will that then help? Not necessarily, because it doesn't take into account the local phenomena that happens when you have, for example, holes. Yeah? And they play a big factor here. Yeah? The approach we follow is we will find out how the copper layer thickness looks like without. So we know exactly where you have highs and lows. And then, based on technology that obviously we have developed, we are able to generate, let's say, a set that is as good as possible. Yeah? Now, having that set, we should also think about the following. We do copper balancing here to make the plating more uniform. Okay. Now, copper, let's say, copper padding or whatever you want to call it, is sometimes also added to avoid warpage and these kind of things, because you need to have more uniform, let's say, distribution of copper to avoid, let's say, issues that are not plating related, but that are related to having deformed shapes of the plating, etc. Yeah. So what you could do is create a design, put some kind of uniform plating on top of that with some more spacing, I would say, yeah, and then tell the Elsica software like, okay, these areas I have added as copper areas that are not part of the electronic circuit, and we can manipulate them. So what we will do is we will, let's say, increase in some areas the density of those copper that you added to ensure that you have, let's say, a good uniformity. Actually, if I go back here, I think it's an example of that. So it's something like you see here. Yeah? So you have a kind of, let's say, pretty uniform basic hatch, but then we will increase even more let's say, the copper density here, because there is more active surface required to compensate for, let's say, these corners that you see here. Is that a bit an answer to your question? I'm trying to be a bit, let's say.
Yeah, I think one of the things I got from that was, you're talking about holes, and that's kind of what I was thinking was it's the whole surface that adds to the top surface of that layer. Now,
Absolutely.
if you're doing this on an inner layer that doesn't have a microvia, then you don't have those holes, and it's a simpler kind of approach. But clearly for HDI designs and outer layers, you're going to have that additional surface area in there that you have to compensate for. So I get it.
Yeah, but also for inner layers. So I mean, obviously, plating is only. I mean, we for plating that means you let's say iterate. So it can very well be that an inner layer passes a plating step and is then brought back to the beginning. It's pressed again between two other, let's say, laminates and things like that. So it depends a bit, of course, on the total process. Yeah.
Right. If it's got plate up steps for those microvias or any sort of inner hole like a blind and buried or anything like that, then it would be affected. Yeah.
Yeah, exactly. Yeah. But also here, since we're talking about holes, just as a side note, and again, we do not have time to go into all the details here. So what we do here and what you see here is the layer thickness on the surface. Yeah. Obviously, we are also able to compute the layer thickness inside the holes, and the presence of these holes is taken into account to compute the layer thickness on the top. But I think we all agree that if we see that certain areas have not enough thickness on the surface, you can be very sure there will be not sufficient thickness in the holes either. Yeah. So that's a first step to check. Yeah.
Does this help with dimple control as well for plated holes?
We obviously check the holes as well, but there is like, how to say, you have the how to name it. So you have the plating, I would say, let me call it the normal plating, and excuse my language here, I do not know how to pronounce it differently here, where we basically have, for example, a hole where you thicken the wall of the hole. Yeah? But in the end, there is still a hole, and the goal is to, let's say, fit some component or whatever on top of that. Yeah? That's one thing. The other thing, and I think that's what you're referring to now, is via filling, where you actually start filling up the entire, let's say, typically blind via, where you then want to have good connection and you put a component on top of that. And then, of course, the dimple can arise as well as a void that you may have embedded in the inside the via filling process itself. Yeah, so that's a very complex process. It's also typically with specific chemicals, etc. That's something we today do not yet fully support, but we're working on that, and that's coming for sure. Yeah.
Thank you, Joe. Thank you, Robert. There's still a couple of more questions we can try to get to if folks can stay a few minutes past our time, but if you must drop, I understand. Thank you for your attention. Let's if Boban George, are you still here? Yeah, I see you. If you'd like to ask your question, we can do that.
Yeah, my question is simple. Do we provide this tool as a service, like on need basis for each PCB?
Well, the tool is available as a software. Yeah. So we as a company, we obviously, I mean, if a customer comes to us and says like, hey, I would like to have a certain thing analyzed, we can do that too. So we also have an engineering team that can help with that. But in this case, the main goal is to provide this tool for local use in companies, because typically, at least so far, my experience is that people are not very keen on sharing designs externally and prefer to keep everything internal. Yeah? And that's the reason to provide this. Now, just for you, because I feel a bit an outspoken concern, like how difficult is this to use, etc. The good thing is this is extremely simple to use. There is no need for, let's say, certainly from the designer point of view or the CAM point of view, you don't need to be a plating expert. You don't even need to know what plating is. Yeah? The software is, like I said, if it's integrated in your CAM or ECAD environment, it's just one button. Yeah. Of course, if you would like to use it as a fabricator, then yeah, clearly you need some plating knowledge. But I'm talking plating knowledge. I'm not talking formula knowledge. So there is in the software nowhere a need to enter a formula or something. So you can very quickly get up to speed.
Okay, thank you.
And can I add one more question to this?
Sure, go ahead.
Okay. Typically, how long it will take for an 8-layer to analyze and give the result?
It's of course, yeah. I mean, 8 layers, layouts, etc. I mean, does it mean we only look at the plating step itself? So if your 8 layer only has, let's say, a plating step for the outer layers, for us, it's that's it. Yeah, we just do the outer layers. So it's difficult to predict. But to give you an answer, if we talk about the PCB itself, so the PCB balance, like we call it, so checking a PCB layout or a panel layout, that is typically order of magnitude a few minutes to 10 minutes, 15 minutes. Yeah, that's it.
Okay. Yeah,
if you want to do a full production, that of course, yeah, that can be more complex. Then we're talking, let's say, typically 10 minutes till half an hour, roughly.
Thank you so much.
Daniel, if you're still available.
Just wanted to ask briefly about the use of digital twins or these kinds of models for a bigger optimization, right? There's all sorts of ways of optimizing. I mean, you outlined quite a few with the balancing effort, but some of them may involve trade-offs with the processing time or whatever, modifying the equipment, et cetera, et cetera. So you'll need certain kinds of detailed information to be successful there. I just wondered from the total, I don't know, 100,000 foot level, do you think that these kinds of twins are going to allow for people to really optimize the pieces of this thing that they need to get to the most economical production? Thank you.
Yes, thank you for that question. So yes, I'm convinced that that's available because it's already applied. Yeah. Now, of course, to then maybe, let's say, soften that a little bit, there is always like, I'm sure you know the 20/80 rule. Yeah. You always have to look what is economical. Yeah? And let me clarify. So if I have a certain PCB and I'm just saying something, 10 PCBs on a panel and I would like to optimize that, but I only have to produce 50 and I have a scrap rate of 20%. Well, I mean, that's too bad, but maybe just produce then a little bit more and you're done. Yeah? If, however, I'm going to produce 5 million of those, it's extremely important I optimize to much better extent here. Yeah. So it's how to say, where the threshold is, where you say like, okay, I still want to spend time and effort on further optimization compared to I can live with what I have here today. Yeah, that is depending from case to case. Yeah, but it for sure is possible. Yeah, and we also have let's say. Customers, and I want to be a bit vague here, yeah, that also optimize their, let's say, infrastructure with this. Yeah? So instead of building or taking, let's take an example from a fabricator. If you consider a new electrolyte, or you would consider a new anode, or you consider building a new line with new dimensions, or you consider a new pulse rectifier, you better be sure that when you buy it and you build it, that it works. Yeah. So that's something you can definitely check with the software prior to.
But as you, Robert, as you build this tool, you gaining now all this knowledge. Does that get embodied in the tool, or does that only stay locally with the customer of the tool?
You mean the mitigation strategy they apply, or the information about the digit? Yeah.
Yeah, the detailed knowledge of how many holes you should really have, or how many extra printing features do you need, et cetera, et cetera.
Well, that's of course that remains within the companies. Yeah, we do not have access to, so we have nothing like a logger or something to see what our customers do with that. So how shall I say, the entire thing of optimization, etc., it's still something that is, let's say, triggered by the plating expert, if you want. Yeah? So whatever he has between his ears and he would like to check is something he can enter into the software. The only thing that we did apply And automated is the process of the copper balancing. Because here we're more in an area where, let's say, the operators are typically not extremely, and with all respect, so knowledgeable about the plating process itself. They're more focusing on the electronic design, for example, or on the cam layout, etc., but not necessarily the plating expert. And that's where we felt like, okay, here we can do that. That's also a bit, I mean, it's still complex, but a little bit less, well, a lot less complex compared to being in a real production plant where you have, let's say, a zillion amount of parameters to play with. Yeah, where in an ECAT or a CAM environment, you're a bit less, better limited.
Yeah, thank you very much.
You're very welcome.
So we have one last question from Shekhar, who had to drop already. So I will read it. He asks, can the simulation platform predict plating thickness uniformity across complex PCB geometries or high density interconnects?
Yes, definitely. So the complexity of the PCB is, and that may sound a bit strange, but the complexity of the PCB does not even have an impact on the, let's say, the calculation speeds to produce the results. But if the question is like, can we, for example, work with, let's say, very thin traces like 20 micron or even below that? The answer is yes, we support that.
Okay, very good. I have no more questions in the chat. I will ask anybody that is still on the line, if you do have a question, as long as Robert is willing, you can raise your hand and we can try to ask them. Otherwise, I will end up closing the call here. Let's see if there's any last minute questions from anyone. Looks like not.
Okay.
So,
now, if something would pop up later, feel free to contact you, Mark, or me in the way that you like it. Yeah.
Yeah, absolutely. You can send a note to me, mark.s@inemi.org, or to Robert directly, or just really info@inemi.org. It'll get to me eventually. There's Robert.
My email address is here.
So there you go. Perfect. So Robert, thank you so much for your time. This was great. I think we got a lot of interest in it. We might have to bring you back for another deep dive. I think there was a lot of interest from folks here. That's great. Good to see.
Well, if the feedback you would get, Mark, would be, let's say, to indeed have another session on certain specifics, because I mean, it's a specific and broad area at the same time.
Yes.
Let us know, and we will definitely, or I will definitely do my best to support you with another session or multiple sessions.
Yep, that's awesome. Thank you so much, Robert.
Thank you very much, everyone.
For your attention. It's much appreciated. Thank you all. Have a great day.
Bye-bye.